This time we're going to learn how to calculate and then interpret a z-score, something that's very interesting and helpful and useful for giving context to an individual score or datum. We saw last time how giving meaning to a datum is very important and useful in terms of percentiles. We'll get back into that later, but for this time we're going to learn how to calculate a simple measure for a score that gives us an idea of just how well it fits into its data set. As a really brief example, maybe this will be helpful. Let's say I come up to you and I say, hey, I just got a score of 34 on this test. And then you go, okay, I don't know what that means. What's a 34? And what you're really asking is out of what? Like what was possible, for example? What was the possible range? Also, you want to know how did other people do, right? So if I say, hey, I got a score of 34, you go, I don't know what to do with that. I say, and the average score on the exam out of everybody who took it was 30. Now you know you should respond positively and say, oh, you did better than average. That's something good. Now, that's great. What would also be more useful is if I told you how much better I did than the mean, right? Which would be the standard deviation. So that's a very interesting way to start looking at scores, and it gives a lot more meaning to an individual score when you know not only what was the average compared to your score, but what was the standard deviation of the people who also took that test, for example. And so a very nice way to do this is to convert a score to a z-score. It simplifies all of these pieces of information and puts it into one single score in terms of standard deviations. So I will show you how to do that now. This is the equation for a z-score. It's very simple. Again, we've seen all of this if you've been following these videos. So all we've got here is the z, meaning that's the score, the z-score that you're calculating, and this is how we get it. We take the individual score that I'm interested in, right? So for example, in my little example, I said my score was a 34. That was the one score I was interested in the entire set. This is, of course, the mean, bar x, nothing, the mean from the data set that I derived my score from. And then, of course, the SD is the standard deviation of the data set that I am comparing myself to. Okay, very straightforward. So we'll now try it with a very brief example. Let's say, very similar to what I just said, that Scott comes in and he says, hey, I want to know how I fit into the class, for example. Scott just took an exam and he wants to know how he fit into the class with this score. And so we'll convert it to a z-score for him, and then I'll show you how to interpret that. He scored a 41 on an exam, and the class average was 36, and then the standard deviation was 6. So now all I need to do is put those three pieces of information into my z-score equation, like this. Of course, this is what I'm looking for, the score that I want to convert into a z-score, which was his score, a 41. It has to be a single score. Then I'm subtracting the mean. In this case, that was 36. Then I'm dividing by the standard deviation, which was 6. Now, of course, the math from here is pretty straightforward. All we do is take the 41 minus 36, which is, of course, 5, and then we divide that by 6. 5 divided by 6 is 0.83333333, and on forever. But we'll simplify it to just 0.83 for our purposes. The rounding won't really make a difference here. So therefore, Scott's z-score is 0.83. Now we need to interpret that and see what that actually means. So let's do that. So let's imagine that we have a distribution here of, in this case, z-scores, okay? So this is called a z-distribution. In other words, what we have is this is not the test scores along the x-axis. We've changed the metric. The metric is now no longer the test scores of 0, plus 1 point, plus 2 points, plus 3 points, and so on. But these are z-scores. So z-scores are fundamentally in standard deviation units. Okay, so in other words, the distance between this and this is one standard deviation. The distance between this and this is one standard deviation. Okay, so in other words, a z-score of 1 means one standard deviation away from the mean. Plus 1, at least, is above the mean. So because Scott had a z-score of plus 0.83, that means that he scored about right here, or 0.83 standard deviations above the mean of his distribution. So now that's pretty interesting, because I can say to Scott, Scott comes into me and says, hey, I got a 41 on the exam, and I can quickly state, well, that means that you scored 0.83 standard deviations above the mean in the class. And then he can say, well, that's pretty good, right? And I could say, yeah, that's actually quite good. Now, what would be even more informative in this case is I could give him the percentile in which he fell in the classroom, but that takes a little more conversion, so we'll do that later. For now, let's just keep working on these z-scores. So now let's try another example giving you a negative z-score. So let's say Scott's classmate Tim comes in and he says, hey, I scored 30 on this exam. Well, now let's create a z-score for Tim and just see how well he did. So one thing you can quickly note is he clearly got below the mean, right? So Tim did not do well on this exam. 30 is below the mean of 36. We're keeping the same mean, right? But now we want to know how much worse did he do? How far away from the mean did he do in terms of standard deviations? So that's what we do here. So his score was 30. We kept the same mean, which was 36, and the same standard deviation for this population. 30 minus 36 is negative 6. Negative 6 divided by 6 is, of course, negative 1. So if Tim's z-score is negative 1, we now need to see how that looks. Now, obviously what that means is a negative 1 is one standard deviation below the mean of the population. So once again, it's the same distribution of z-scores, and here is Tim's score. So Tim scored one standard deviation below the mean of the population, which in this case is the class, and Scott scored about right here at a 0.83, which is above. So a couple of things we can say. Not only did Tim do worse than Scott. We knew that anyway because he had a lower score. But Scott scored above the mean. He scored almost a standard deviation above the mean, whereas Tim scored a full standard deviation below the mean of his population. So that's kind of what we can do so far, and it's very useful. Now, a couple of things you could do beyond this, even if you wanted to. Some things that I'll do in class when we have more time is I'll say we can actually compare apples to oranges using z-scores, because z-scores look at you in your context to your population. So now what I could do is compare somebody in their population compared to somebody else in their population. So for example, if you wanted to take like running times or something, if you got two racers and one's a male and one's a female. Male average running times and female average running times are different just on average. And so let's say a female and a male want to compare themselves to each other, and that would be unfair. That would be sort of inherently unfair. But what we could do is say within male runners, here's where you fit to the male, and to the female, within female runners, here's where you fit in your comparison. And now that would be more interesting because we could see, is the female doing comparatively better in her population compared to the male in his population? And we can do all sorts of things like that with z-scores if it's interesting and if it actually makes some sense. Now, there are, of course, some caveats to all that, but that's good enough for now. Okay, so real quick recap. A z-score is a very nice conversion that gives us more meaning to a single datum, a single score, and it gives us the context of that score within its sample or its population. And so all we really need is that score. We need a mean for the population from which it came, or the sample from which it came, and the standard deviation from that same group. Now, of course, what we can do at this point is once we have a z-score, we can convert it to a percentile, which we talked about last time, talking about percentiles. So in the next little lesson, I'm going to show you how to do that, how to convert one z-score into a percentile so that you can give a little more nuanced context to that score itself. So we'll do that next time, and I'll see you then.